Okay, great. So hello to everyone and welcome. As Ariel said, my name is Melanie and I have the privilege of being the software lead for the tremendously talented data processing system team for SOFIA. So I've been working on SOFIA pipelines for almost 10 years now, but we've only just been able to provide our software publicly as of last summer. So this is a topic close to my heart. I'm so proud of what we've built and so happy to have a chance to share it with you today. So later this week, the other talks will get into details of how to use the pipeline for specific instruments. So today, I just want to give you more of an overview of the pipeline package. So what it is, how to install it, and why you might want to. So first, there we go. First, what is it? So SOFIA data reduction software is all published together as a single Python package that we call SOFIA Redux. It contains all of the code, configuration, and reference data that you need to take raw data straight off the instrument and remove instrument artifacts like bad pixels and gain variations, as well as background artifacts like the entire bright infrared sky. The pipeline also calibrates data to physical units and combines separate data sets into composite products that are useful for your science, like mosaic images, spectral flux cubes, or polarimetric vectors. Currently, the public pipeline supports forecast, FIFI-LS, FlightCam, and Hawk data in all observing modes. For XEs, the internal pipeline is not yet, was still implemented in IDL. So we're working now on porting it to Python, so it can be incorporated into SOFIA Redux package. We're hoping that'll be done and available to you within the coming year. So some more information about the SOFIA Redux package. My team supports both internal software releases, which are deliverable to NASA, and as well as public releases, which are deliverable to you. So to manage this process, we develop our pipelines internally, and then we push the public code out to you. Our public platform is a GitHub repository shown here. Okay. So our code is open source. It's licensed under permissive BSD 3-clause license, which means that you are more than welcome to fork our code, modify it, experiment with it, maybe even improve it. If you develop something great, we'd love to have you share it back to us. But because our development happens internally, we can't actually merge your code directly on GitHub. So we'll review it, we'll merge it internally, and then we can push it out with the rest of our code. So if you have something to share with us, please file an issue on GitHub to let us know. As you can see from this screenshot, nobody is actually talking to us much on GitHub yet. But don't let this intimidate you. Your feedback is welcome. If somebody in this meeting wants to log on right now and file an issue, that would be doing a service for the community by breaking the ice. The other option for pipeline support or questions is to send an email to the SOFIA help desk. Email is shown on the screen here. So if your question relates to a particular data set rather than to the pipeline software itself, that's the route I'd recommend. Okay, so how do you install the SOFIA pipelines? If you're a casual user or you just want to check it out, it's pretty easy with standard Python installation tools. So either pip or conda should work just fine to grab the latest pipeline version. But if you expect to work with the pipeline often or really delve into the code, I would recommend installing from source instead. This is the installation path that everyone internal to SOFIA uses, so it's likely to be the most well-tested and robust route, and it will let you keep all your code and calibrations up to date as we push the latest out to you. If you have Anaconda and Git installed, this little snippet here, these 4 lines on the screen, will set you up with a copy of the Git repository, a Conda environment to work in, and an editable install of the SOFIA Redux package. So then all you have to do is just git pull from your repository, and that will pull the latest whenever you want it. Separate from the code installation, we have some reference data libraries that were too big to fit into the code packages. So first and probably most important, there are atmospheric transmission spectra that are necessary for optimal telluric correction for spectroscopic data. These have to be separately downloaded, whether you install them from source or from pip or conda. There are also some standard flux models that are necessary if you're generating your own spectral calibrations, and some auxiliary data for flight cam reductions. These are included in the source package on GitHub, but they're not in pip and conda installs because those tools require that we keep our software packages smaller. All of this is explained in the Getting Started docs that are online. So when you are ready to install our pipelines, I highly recommend starting there. Okay, so backing up a little bit, why would you want to install our pipelines in the first place when SOFIA already provides science-ready reduced data products in our archive? And personally, I think there are a few good reasons. So I'll go into each of them in the rest of this presentation. First, and probably foremost for this audience, the pipeline package can help you understand your SOFIA data better and get you to a solid science analysis faster. In particular, we now have extensive documentation posted online about exactly what our pipelines have done to turn the raw data into the science products that are in the archive. But in my experience, not everyone loves to read the documentation. So if you're more of a learn by doing kind of person, I'm not sure there's a better way to learn how your data was reduced than to grab the pipeline and do it yourself. So intermediate data products from the pipeline are produced at every step, and they're available for your inspection. Also, we have a number of visualization tools that are packaged with the pipeline that we developed primarily to support internal quality analysis. These are available to you as standalone tools, and they can be really helpful in accessing and understanding your data products more quickly. So I'll go into each of these 3 points more in just a sec. Oops. There we go. So first, for the documentation online, I'd particularly like to point you to the user manuals for the pipeline. There's one for each instrument, if you're not already familiar with them. So they contain useful things like flowcharts that describe the data reduction steps, and also tables of all the intermediate and final data products from the pipeline. So if you've ever wondered exactly what the files are that you downloaded from the SOFIA archive, this is a great place to start. For running the pipeline and inspecting the intermediate data, I'll give a couple quick examples of what that looks like. First, when you start up the pipeline interface, the first thing you do is load in raw SOFIA data. And the pipeline immediately knows what to do with that. So it will pull up all the correct pipeline steps for you, along with all of our favorite default parameters for every pipeline step. So all you have to do is press go to reduce your data, or rather click step to run the next step, or reduce to run them all at once. For each step, you can inspect the parameters, you can read the log as it runs, and you can look at the files that are written to the disk. The pipeline interface also incorporates a number of custom visualization tools that will let you look at the data as it's produced. So there's a spectral viewer for spectroscopic modes and an interface to DS9 for image products. These are both fully interactive, so you can directly inspect what the pipeline has done to your data right in the middle of your run. Okay, so I have a quick video demo here of what it looks like to run the pipeline with a forecast imaging reduction. So I know this video is a little bit small, but I'm hoping it's okay because I'm not going to get into the details today. So see the later webinars this week, or else the pipeline tutorials that are posted online for help with the details. This video is more just to give you a flavor of what working with the pipeline interface looks like. Okay. So starting up the pipeline interface, the first thing you do is load in some raw data files. These ones happen to be forecast imaging files, so the pipeline will pull up forecast imaging steps. Okay. So each of these steps has parameters that you can inspect and edit. And there is some summary information about all of the files that are loaded gets compiled together into this little table, so that will give you a quick glance at a quick description of the data that you've loaded. There is also a log window that shows the data reduction status as it goes. So to run the pipeline, we can select a breakpoint for the steps and then press step. It will run through all of the intermediate steps up to that point. When processing finishes, we can turn on the DS9 interface to show the data. And this shows the intermediate data that's currently available. The data are locked together in the image reference frame, and they look pretty well aligned. But we can also lock them together into the world coordinate system, so in RA and DEC. And zooming in, it actually shows that there's a little bit of an absolute position offset between these data, which is a problem for the registration algorithm because it uses the WCS by default. So we can open up the parameters and select centroid as the registration algorithm instead, and then run the step. The data will be redisplayed. And then you can see that it's now pretty well aligned. So now we can step the pipeline through to the QAD step to merge these 4 images into a single image. And now we see that we have a better signal to noise image with no loss of resolution in the central source. Okay. So these same tools that are integrated with the pipeline are also available outside the pipeline interface. So for example, if you're not interested in running the pipeline, but you have some SOFIA data to look at, you can start up these tools in a standalone context. So this tool on the left here we call the QAD for Quality Analysis and Display. This gives you point and click display access for your FITS files. So this tool will work with any FITS file, but it has some special handling for SOFIA data. For example, the highlighted file there is a forecast spectroscopy product, and the QAD knows that there is a 2D spectral image to display, and it throws it up into DS9 and adds some helpful overlays using header information that show where the pipeline placed the extraction aperture. It also knows that there's an associated 1D spectrum in this file, and it automatically pulls it up in the spectral plot viewer with proper calibration and associated error values and transmission data. And that's just by double-clicking the file. So I have another quick demo video here to show you the scope of the tools that are in the QAD tool. Oh, before I start though, I haven't actually shown it in this video, but there is also a standalone interface to the spectral viewer with this tool, if you're only interested in looking at your spectra. So this tool is started by the command eospec, which is for the Eye of Sophia spectral viewer. Okay, so we start the QAD from a directory that contains some SOFIA data. It pulls up this little browser window that lets you poke around at the contents. And you can filter this display to particular kinds of files. In this example, we'll look at merged forecast files, which is an intermediate forecast imaging product. So we can select a file and pull up its header in this text window. We can look for particular strings within the header, and we can also filter the contents to see just the lines that contain that string. If we then select multiple FITS files, we can load them all into the header viewer at once. We can filter the contents or put it into a table for easy comparison. Okay, so back to the browser interface. If we double click on an image file, it will automatically bring up DS9 with some useful display presets. Then if we select multiple files at once and hit enter, it will bring them all up in DS9, all tiled together and locked for use for comparison. There are some analysis tools that are built into the QAD. So clicking the little scissors icon in the browser window will start the ImExam tool. So these commands for analysis are launched from the DS9 window. You use the keyboard. So the options are printed to the terminal, and you can access this help message at any time by clicking H over DS9. So here we're going to click A over a source, and this is going to do aperture photometry at that location in all of the loaded frames. The results for the photometry fits are printed to the screen. So we hit Q to end the ImExam session. And then there's a couple other tools that respect DS9 regions. So if we use DS9 to create a region and then relaunch ImExam, we can hit S over that region. And this will do some statistics, print them to the terminal, and bring up this histogram of the data that's within that region in all those files. So there are some settings that we can use to control these plots to make them a little bit more useful. We can stick all the plots together. We can modify the histogram range. So after doing that, ImExam is still active. We can clear the plots with C, then hit S over the source again, and that will bring up the modified plot. There's another tool which you launch with the key P, and that will do a pixel-to-pixel comparison across all of the loaded images in DS9. Okay, so now let's look at some forecast spectroscopy files. We'll reset the filter to look for all FITS files and select a spectroscopy product. So this one contains a 2D spectral image that is loaded into DS9 with the aperture overlays. And then the 1D spectrum is pulled up into the spectral viewer. The number of tools that we can use to look at the data from this viewer. So we can zoom into the data, we can do some simple profile fits to features in the spectrum. And then there's a control panel hidden over to the left right now that if we expand, we can do lots of other things to inspect the data, change the plot features. So for example, change the units or load in a transmission spectrum to overplot with the data. Okay, so now let's look at some Hawk polarimetry data. So when we double click on the final polarization map, it brings up the first extension by default, but of course other extensions are more useful for polarimetry. So we can pull them all up together in separate frames in DS9 by changing these display parameters. We can also bring them up into stitch them together into a cube in DS9 so that you can pull them up in a single frame and then flip through the cube to find the extension that you need. Okay, so another trick we can do with the QAD is to overplot DS9 regions along with the FITS image. So here we have a .reg file which contains the polarization vectors for this pol map. Selecting them both together and hitting enter will overplot the DS9 regions on top of it. And one last trick on a Mac, anything that is not a FITS file or a region file gets tossed to the Mac open command. So if you have your PNG images like this preview image that is the final step of the pipeline, you can just double click on it and we'll open it up in preview for you directly from the QAD. Okay, that is the whirlwind tour through the pipeline interfaces and visualization tools. So I haven't remotely covered everything that's in there. So if you have questions or want to know more, ask me or see the documentation or file an issue on GitHub. So moving on to another reason why you might want to install the pipeline. You might want to improve archival data products. So data from recent flight series are most likely absolutely fine to use as is. Our expert science QA staff use the latest pipeline versions to reduce and inspect the data before they're archived. But older data in the archive might predate the current pipeline versions. So it might be missing out on some of our latest improvements. So here's a few current examples that I know about. One, the FIFI-LS team has been hard at work updating all the historical raw data with newly available measured water vapor values. So using these to re-reduce your older data can help improve the telluric correction in the final data product. They're working on doing this reprocessing themselves, but we haven't gotten to all the data yet. So chances are good if you're working with older FIFI-LS data, it would benefit from reprocessing with the current pipeline. Two, when we re-implemented the forecast pipeline in Python from the original IDL, we updated and reorganized all the data products to be easier to understand and use. So older imaging products, for example, had data invariants that were stuck together in a cube in the first FITS extension, but they're now separated into flux in the first extension and associated error values in the second, which is much easier to read and work with in standard tools like DS9 or like Python notebooks. And three, the FlightCam instrument has been retired, so there's only archival data available from that instrument, and all of it was produced before the Python pipeline was implemented. So if you want to look at imaging data in particular, I highly recommend downloading the pipeline and re-reducing the raw data, because we've made a number of significant improvements since the IDL pipeline. So for example, on the left here is an archival data product for a flight cam observation of NGC 2023, produced with the IDL pipeline. And on the right is a product made with the current pipeline. So you can see here there are improvements to the background corrections, to edge effect handling, to registration between separate images used to make this QAD file. And the final image is rotated to a standard north-up, east-left orientation, which makes it much easier to compare to other data sets. All right, why else would you want the pipeline? In some cases, you might want to customize your data reduction to suit your science. So archive data is typically reduced with default pipeline parameters unless the QA scientists have a really good reason to deviate from them. But your science might benefit from non-default choices. Like, for example, the pipeline has an optional ability to subtract values from an identified background region in Hawk scan data. And this can help correct for negative fluxes in the output maps. But it doesn't do it by default. You have to tell it where the background region is. Or there are options in the pipeline to allow you to rebin your Hawk polarimetry data. You can, for example, decrease your resolution to get higher signal to noise in your vectors. Or for forecast or flight cam spectroscopy, you might need to tweak the wavelength calibration or improve the telluric correction or recalibrate with a standard that was closer in time to your data than the flight series average. And there are pipeline tools to help you with all of these tasks. Or one last example, if you have a bright compact FIFI-LS target, you might be missing flux at the compact core of the target with default map making parameters for the final spectral cube. And there are some optional parameters you can try to do a better job at peak flux recovery. So to illustrate just a couple of those, here is an example of Hawk data that is re-reduced with different binning parameters. This may be a little hard to see over WebEx, but the middle image is the default resolution. The left image is reduced with pixels twice as large, and the right is with pixels half as large. So rebinning like this might help you inspect the robustness of your vectors to different binning parameters, or just to sample and report them in the way that you prefer. Also, here's an example of a bright compact FIFI-LS source. This is M82, and it's reduced with default parameters on the left, and then two kinds of adaptive smoothing parameters on the right for the final spectral cube step. These images are all locked to the same flux display scale. And then in the spectrum below, which is taken at the same spatial pixel in each of these flux cubes, you can see that the default reduction with a static kernel smooths right over the peak flux. The peak flux is significantly lower with a static kernel than when we use an adaptive kernel. So allowing the kernel to vary recovers the peakiness of the source much better. Okay, one last reason why you might want to download our pipeline software. Maybe you have some software development of your own to do to support your scientific analysis. So the primary purpose behind developing our pipeline package was to reduce SOFIA data, of course. But in doing so, we've actually generated extensive libraries of highly performant scientific Python algorithms. And the problems that we've solved for SOFIA purposes might be problems that you faced in your work too. And maybe we can help. So for the last part of this talk, I'm just going to give you a quick tour through the kinds of code that we've developed, and maybe some of it will look like things that you need too. So first, we have a calibration module, which is intended for flux calibration of imaging data. So this module contains some general purpose imaging flux calibration routines, as well as automated source detection, profile fits, and aperture photometry. We use it to calibrate Hawk, forecast, and flight cam imaging data, as well as provide the photometry tools that are linked to the QAD visualization tool. But it could be extended to calibrate other instruments, or it could be used to support other photometry needs. The instruments module, this contains instrument-specific handling for artifacts and procedures that are unique to SOFIA instruments. So if you're working with non-SOFIA data, maybe you don't need this module, but it might still be useful as a detailed working example of how we use all of our other tools. The pipeline module, this implements the GUI interface that we saw, and also the batch processing tool for all of our instrument pipelines. This module was always intended to be generic and extensible to run any sequence of processing steps that you can dream up and display them any way you please. So all you really need to use our interface to run your favorite steps on your own favorite kind of data is to make a new reduction class that knows what to do inside each step. And this is how we implement all of our instrument pipelines. There is a reduction class for each kind of data that knows what to do with it. So there's a forecast imaging class, there's a FIFI-LS class, and that's really pretty much it. The GUI and the batch interface don't need to know anymore, they just work. And we found this is a really useful model for keeping a consistent interface on some really wildly different backend processes. The scan module implements algorithms to derive source flux from continuously scanned far infrared data, so separating source from gain and background without having to do time-consuming separate observations of empty sky regions. So we use it now for the Hawk instrument only in scan mode, but it's also very general and it could be extended to work with many other instruments and different kinds of data. The spectroscopy model has tools to rectify, calibrate, and extract 1D spectra from 2D spectral images, including handling for long slit or cross disperse spectra. So we currently use it for long slit spectra from forecast and flight cam only, but we do expect to extend it to XE's cross disperse spectra very soon. The toolkit module. This contains general purpose scientific and numerical processing algorithms in support of all of our other modules. So it includes image processing and manipulation tools like rotation, warping, bad pixel masking, and interpolation. Also tools for convolution, fitting, and interpolation, general interpolation. And it also includes a module for resampling and mosaicing irregularly sampled in-dimensional data with associated errors. And if that last one sounds kind of complicated and also kind of awesome, that's because it is. We think it's unique in the scientific Python ecosystem, and it's very powerful. So I just want to take a second to highlight it. In our pipelines, we mostly use the resampling module to handle sparsely sampled data, like this FIFI-LS observation, again, of M82. This point cloud here on the left was compiled from 108 separate raw FIFI-LS files. And the resampler turns this data cloud into this beautiful spectral flux cube on the right. So this little movie is stepping through wavelength slices of the flux cube, showing the spatial flux distribution at wavelengths near 158 microns. So the resampler, what it's doing is a fully three-dimensional polynomial fit to the data near each output grid point. Within a defined window, applying a distance-weighted smoothing kernel and also weighting by the input error values on each input sample. And it's fast. It's implemented with some clever data blocking tricks. It uses Numba for just-in-time compilation to get C-like speeds for Python code. And it's heavily parallelized to grind through the data as fast as possible on whatever machine you've got. So in our pipelines, we also use this resampler for mosaicing separate Hawk images together and for making spectral cubes out of forecast slit scans, which is similar to FIFI-LS data. Okay, but it's a very powerful and general tool and could be used for lots of other things too. Like for this example, fitting to noisy 1D data with an arbitrary signal function, or working around missing data, including absolute wizardry, like this example, reconstructing images from very corrupted data sets. It's probably a little hard to tell from this slide, but the image on the right, the cat picture, is reconstructed from the image on the left, which is 70% NaN values and 30% little scattered RGB dots. Or if you've ever wanted to do that thing they do on TV where they take a grainy image and say enhance, that's what the resampler can do too. So all of these three examples are straight from the docs for the resampling module. So if any of this sounds useful to you, maybe go take a look. Okay, last module in the pipeline package. The visualization module contains our spectral viewer and also some other tools to automatically generate the summary images at the end of the pipeline run. And that module in particular might be a good place to look when you need to generate plots and images for your SOFIA papers. And that is just about everything I wanted to say today. As a final comment, I'd like to point out that the SOFIA pipelines are the work of dozens of developers and scientists over the course of SOFIA's lifetime. So while I have the floor, I'd like to say thanks very much to every single person listed here on this slide. And if I've missed someone, it was definitely not intentional. So if it's you, please let me know and I will add you to the credits page that is at the link at the bottom of this page. In addition, I want to acknowledge several external packages that our pipelines owe significant debts to. One, AstroPy, in addition to being a significant dependency of ours, is also an absolute luminary in open source scientific code. And as such, we've followed their model as closely as we possibly can in packaging and documentation structures and coding style and standards. Two, Crush is a Java package developed by Dr. Attila Kovac that contains the first implementation of the scan modules for Hawk data, as well as support for lots of other instruments outside SOFIA. And three, Specs Tool is an IDL package originally developed at IRTF for the Specs instrument that was the basis for the algorithms in our spectroscopy module. Okay, and now that is it from me, so give me all your questions.
Thank you so much, Melanie. Question from Riwaj. Are there video tutorials available for interactive viewing of Hawk Plus data with the visualization tool? Similar to what Melanie showed, but more detailed.
I'm not aware of any videos that are available right now. That is certainly something that we could develop, and if it would be useful, we can take a look at that.
Well, there will be one on Thursday.
Oh, that's true.
Yeah. So, and if you can't be there on the Thursday, it will be recorded and put on the website. I don't see any more questions, but I do have one. Usually I go straight to level 3 and 4 data and not to level 0 raw data. So to run the pipeline, should I download all level 0 data associated to a given AOR? And those are all FITS files?
Yes, whether it's level 0 or level 1 actually depends a little bit on the instrument. Hawk raw data is level 0. For all the other instruments, it's level 1. But yes, you should download all of the raw data associated with your observation and look at it together. Do be aware that there are frequently QA notes that are associated with particular files. So some of the raw files might need to be excluded from your reduction after you download them. But yes, if you're running the pipeline, I recommend starting from the raw data.
Okay.
The pipeline does have the capability to restart from intermediate products, but because the intermediate products drift over time, the intermediate products that are in the archive might not be readable and usable by the current pipeline. So starting from raw data is best.
And can I select a subset of raw data associated in an observation that the pipeline will not show because some files are missing? Or
no, it will reduce whatever you give it. So that means that it's kind of on you to decide what an appropriate data reduction grouping is before you give it to the pipeline. The pipeline won't decide for you. It will just try to do what it can with what you've given it. So in particular, if you have different GRISMs for forecast spectroscopy, for example, you might want to, you'll need to reduce those separately. You can only handle one GRISM setting at a time. But if you give the pipeline the full data set for the observation, it will reduce it all together. If you give it a single file, it will attempt to reduce it by itself.
hey, I see Sachin has some comments. Sachin, do you want to unmute? Maybe.
I'm in a public place, so I don't know if you guys hear me well or not.
We do.
But if you do, to add on Melanie's question, for example, if you take a Hawk data, for some of those Hawk data, you need a whole set of observations. So you can't take like half-wave plate data and try to reduce it. You have to have all the 4. And if you don't do it, then the pipeline will complain. It'll give a message saying you need all the 4 half-wave positions. Thank you.
Okay, thanks, Sachin. Another question from Riwaj. Can I use the uncertainty estimate from the pipeline as the final uncertainty, or do I need to add some floor to it, specifically for Hawk Plus? Melanie, do you need more details?
No, I think I understand the question, but not being a scientist, I can't actually answer it. So that is a science decision. But maybe Sachin can speak to it.
Sure.
Did you see the
Uh,
question,
the un-
Sachin?
Yeah, so the question asked is, can I use uncertainty estimates from the pipeline as the final uncertainty, or do I need to add some floor to it? Um, our pipeline has changed over the years, so I'm going to ask first a question to Melanie, and then we'll answer. Melanie, are the calibration uncertainties included in the final product?
No, so the error estimates in the final product are statistical uncertainties only. So there is going to be a systematic uncertainty on top of those error values. So, but that doesn't necessarily mean that you need to add that in. Sorry, go ahead.
So that may help you understand the issue, Rivaj, that, for example, when we have, as Melanie said, we have uncertainty frames in the final product and I can use them, but there may be cases where you'll have to look at your calibration uncertainty and figure out if you need to add that or not. It depends on the case by case basis. It also depends on which instrument you're looking at.
Okay. Thank you, Sachin and Melanie. I don't see any more questions, but I'll wait just a couple of minutes to see if any are coming. Oh, hi, Eric. Question from Eric. What about calibrator images? We need to wrap those in order to process the pipeline. So I imagine those are listed as level 1 and together with the other raw data.
Yes, there are raw calibration images in the archive that you can look up and reduce yourself, although in most cases you won't actually need to. The pipeline includes calibration reference data that is used to calibrate the data. So calibrator images are not necessary for most science reductions. So the way that we do that is our instrument scientists like Sachin take all of the calibrator data from a flight series and analyze and compile it and put together the information into reference data that the pipeline uses. And that reference data is stored along with the code and distributed along with it. So unless you feel there is a problem with the calibration for your particular data set, you shouldn't need to redo the calibrations. Sachin's already done it for you.
So if you take all the level 1 data, and depending on whether or not you included the calibrator data in it, you will get a different output.
Well, so typically calibrator data is a completely separate observation. So for example, for forecast imaging, we take standard observations of flux standards regularly, and those are reduced separately by themselves. The flux information from those observations are then extracted and applied as basically a single number to the science observations. So you typically wouldn't reduce your flux or your calibrators along with your data. So there is an exception to that, which is the Hawk chop nod mode. There are internal calibrator files that are taken alongside the data, which are used to help correct for temporal fluctuations in the detector. So for Hawk chop nod data, you do need the internal calibrator files and you need to reduce them alongside your data, but that's an exception. I believe every other instrument and mode that we have, you just reduce the science files by themselves and use auxiliary reference data.
Okay, so it sounds to me like for everything except Hawk, the calibrator data would be listed under a different AOR ID, so you wouldn't get it by mistake.
Right, exactly. And if you do happen to need it, if you'd like to look at calibrations and how they're done, we can help you find appropriate calibrator observations.
Sachin, you had a comment?
No, I think Melanie just mentioned that if you need data, let us know. We'll give it to you. I can give you an example, Eric, about Hawk data, which I know you have. For example, when we take calibrator data for Hawk below 39,000 feet, those are not really usable because of the high water vapor. So what we do is we usually try to avoid those observations. But in some cases where we don't have an option, we use them because something is better than nothing. So in those cases, you may want to go back and look to find if you have calibrated data that are at higher altitude. And if you do find it, then you may want to re-reduce it. But those are very extreme cases. Most of the data we put in the archive are well calibrated, but there are always edge cases.
Okay, sounds good. Thank you.
Thank you. We had a question about where the talks will be recorded, and I put the link in the chat. So if there are no more questions, I think we can wrap up here. Thank you again, Melanie, and for this great talk, and thank you, Sachin, for helping out with the questions.